Revolutionizing quantum processing, metasurfaces, and graph theory photonics. Here's a brazen claim. The future of quantum information processing might not be buried in bulky machines or error-prone waveguides. Could a single ultra-thin chip replace room-sized optical setups and still achieve entanglement? That's exactly what researchers at Harvard are betting on with Metasurfaces. These aren't sci-fi concepts, but cutting-edge photonic arrays being tested now. Key insights: photo-proof. Recent innovations demonstrate how these nanoscopic structured surfaces can function as robust, linear quantum optical networks. Waveguide obsolescence: their approach bypasses the need for conventional optical components like beam splitters and lenses. Mathematical breakthrough: by mapping quantum photon interactions to graph theory nodes and edges, they can encode entangled states with unprecedented simplicity. For years, quantum computing's biggest hurdle has been scaling photon networks. Those light particles zip through waveguides and mirrors, but building complex quantum systems demands precision that's hard to maintain. Enter metasurfaces, flat devices patterned with light-manipulating nanostructures. Imagine a single chip controlling multiple entangled photons through intricate phase changes, retracing boxes of optics that take engineers weeks to align. The Harvard team, led by Dr. Federico Capasso, achieved what was previously considered theoretical. They created metasurfaces that effectively act as quantum optical chips, creating entangled photon states without the traditional bulky setups. We're collapsing entire optical systems into stable, ultra-thin chips, explains graduate student Carlos Youssef. The implications for scalability are profound. Understanding metasurfaces simplified. Their quantum potential comes from precise nanoscale patterning that manipulates light with less loss than conventional systems. But designing these optical processors isn't just a matter of etching patterns. It requires mathematical wizardry. The team turned to graph theory, the study of connectivity in points and lines, to map quantum states. Think of it like visualizing photon interactions as nodes connected by edges of your circuit diagram. This approach let them predict interference paths and optimize the metasurface structures for specific quantum operations. Why this matters beyond quantum computing. The research collaboration with Marco Lantra's Quantum Optics Lab hints at broader applications. Could lab-on-a-chip setups emerge for fundamental physics experiments? Might these devices enable room temperature sensing systems, outperforming current cryogenically cooled instruments? They're proposing a paradigm shift that challenges conventional quantum optics principles. But here's the controversy. Does this approach truly slice scalability? Or could it introduce new complications like thermal noise or manufacturing limitations? The team acknowledges challenges in scaling to higher photon systems, but claims their graph theory approach provides a scalable framework. It's the missing link between theoretical quantum photonic systems and practical chip-based solutions, argues research scientist Neil Sinclair. As the quantum race intensifies, metasurfaces present an interesting dilemma. They're not just competing with alternatives, like superconductor-based qubits or trapped ion systems. They're redefining how quantum information is processed. Whether they'll achieve the precision and fault tolerance required for practical quantum computers remains to be seen. But one thing's certain. The integration of graph theory with photonic engineering is rescripting what's possible in quantum photonics. Final thought. The research funded by the Air Force Office of Scientific Research and conducted at Harvard's National Science Foundation supported nanoscale facilities sparks tough questions. Could metasurface quantum processors become the preferred platform for distributed quantum networks? Or will they exist alongside conventional systems as specialized tools for particular operations? Sound off. Do you see metasurfaces supplanting traditional optical quantum engineering? Or will they serve as complementary tools? Harvard's ultra-thin metasurface chip. The future of quantum computing explained. Imagine a world where quantum computers can process information at room temperature without the need for bulky and complex optical components. Sounds like science fiction? Think again. In the quest for practical quantum computers and networks, photons have emerged as promising carriers of information. However, controlling and manipulating these particles of light has traditionally required a multitude of optical components, such as waveguides, lenses, mirrors, and beam splitters. These systems are notoriously difficult to scale up due to the large number of parts required and their inherent imperfections. But what if we could collapse all these optical components into a single ultra-thin array of sub-wavelength elements that control light in the same way but with far fewer fabricated parts? Researchers at Harvard's John A. Paulson School of Engineering and Applied Sciences, SAS, have done just that. Led by Federico Capasso, the Robert L. Wallace Professor of Fabric Physician, and Vinton Hayes Senior Research Fellow in Electrical Engineering, the team created specially designed metasurfaces, flat devices etched with nanoscale light manipulating patterns, to act as ultra-thin upgrades for quantum optical chips and setups. And this is where it gets revolutionary. The research, published in Science and funded by the Air Force Office of Scientific Research, AFOSR, shows that a metasurface can create complex, entangled states of photons to carry out quantum operations, like those done with larger optical devices with many different components. We're introducing a major technological advantage when it comes to solving the scalability problem, said graduate student and FACE author Carlos M.A. Youssef. Now, we can miniaturize an entire optical setup into a single metasurface that is very stable and robust. But here's the part most people miss. The researchers use graph theory, a branch of mathematics that uses points and lines to represent connections and relationships, to design the metasurface. By representing entangled photon states as many connected lines and points, they were able to visually determine how photons interfere with each other and to predict their effects in experiments. The resulting paper was a collaboration with the lab of Marco Loncar, whose team specializes in quantum optics and integrated photonics and provided needed expertise and equipment. I'm excited about this approach because it could efficiently scale optical quantum computers and networks, which has long been their biggest challenge compared to other platforms like superconductors or atoms, said research scientist Neil Sinclair. It also offers fresh insight into the understanding, design, and development of optical systems